Here, let's welcome Uma and John, who will be presenting about ZK-SNARK enabled light client and bridge for ETH2 clients. Anyways, give them a quick round of applause.
Hello, I'm Uma, and this is John. And today we're going to be presenting on Succinct Verification of Consensus with zkSNARKs. How do we?
Maybe it's not on right now.
Oh, okay. Yeah, so let's start with a 10,000-foot overview of the multi-chain and cross-chain landscape. In the past few years, there's been a ton of different blockchains that have come online, and they lie on very different points of the trade-off curve in terms of decentralization, security, throughput, transaction fees, etc. And as the number of applications has grown across all these different chains, users generally want to interact between these chains. So some of the things they want to do include transfer assets from one chain to another. And currently, a lot of builders are also exploring other applications of cross-chain interoperability that go beyond asset transfer. And the current space of crypto, like one of its main promises is that it really delivers on permissionless interoperability. And so if users do want to use multiple chains and multiple different ecosystems, then we should allow these ecosystems to operate in a permissionless, decentralized, and secure fashion. And because of this, we believe that bridges are actually very critical infrastructure in the whole space. So what's the state of bridging today? There's a lot of user demand for bridging, and what does it look like? Right now, all the bridges, or most of the bridges, go through very centralized entities. In particular, most L1 bridges today are built on top of a multi-sig architecture where you have a centralized entity controlled by a set of trusted parties that's responsible for watching deposits on one chain and then signing off on deposits on another. And this is really bad because a lot of assets flow through these bridges, and it's kind of this centralized choke point of the blockchain ecosystem. And not only is this ideologically bad, it has real consequences. The multi-sig design is very censorable, and also, practically speaking, there have been a lot of hacks of these bridges. So in particular, there have been many bridge hacks over the past year or so that have resulted in over $1 billion of user funds being lost. And I would argue that this is not only bad for the users, it's actually bad for the whole space in general, because it lessens the credibility of the entire space, and then it leads to downstream consequences like regulation. Okay, so I've talked a lot about the current problems with the bridging landscape, and so let's start talking about solutions. So what does a maximally secure and trust-minimized bridge look like between L1s? So if we were in a world in which on-chain computation was not expensive and we didn't have to worry about those practical limitations, then a really simple and elegant solution comes to mind. We already have a method for a decentralized group of validators to agree on the state of a chain. It's called a consensus protocol. And so we think that if we were able to verify the consensus of one chain in the execution layer of another chain, then we can use the same mechanism that's already being used to agree on the state of the chain for bridging. We call this verification of consensus. And we think that if we're able to do this, then it provides a really great solution for more secure, decentralized, and permissionless bridging.
Yeah, so before we get into how to actually verify consensus in a practical manner, let's zoom out a bit and try to understand the high-level overview of how you might be able to build a bridge or a cross-chain communication protocol over this idea of verifying consensus. So in practice, you're going to have some blockchain like Ethereum, and over the course of its lifetime, it's obviously generating block headers, validator signatures, attestations, and other metadata as part of its consensus process. And this information is normally gossiped over the network to other validators. But what we can also do is we can propagate this information to a smart contract running on another blockchain, such as Gnosis chain. And inside this smart contract, we could theoretically re-implement all the logic we would normally run to verify consensus. And the reason why this is super powerful is because if you can verify consensus, you can sort of keep an append-only list of finalized block headers on this like target chain, such as Gnosis chain. And if you have access to the block headers, as you probably know, we have access to all of these Merkle tree commitments to the entire state of Ethereum, all the transactions that have ever been submitted, all the events that have ever been emitted. And basically, we can trustlessly read any of this data as long as we provide a valid Merkle inclusion proof against these commitments. So why hasn't this been done yet? Well, it's because in proof-of-stake systems, verifying consensus is just a generally very hard problem on consumer hardware with not that much resources. In general, for Ethereum, there's two big challenges. So the first challenge is that there's a lot of validators, and the number of validators is something that you have to keep track in your client, which is trying to verify consensus, because you have to know like the validators' public keys and how much ETH they have staked to like accurately calculate how much their signature is worth. The second problem, in particular with the EVM, is that there are no precompiles for the elliptic curve operations, which the Ethereum 2 signature scheme is based off of, which is this curve known as BLS 12381. So the developers of the Ethereum ecosystem actually recognize that like verifying consensus cheaply is a sort of an important primitive to have for your blockchain to run light clients. So they sort of introduced this easier to verify consensus algorithm on Ethereum, and it's known as this protocol called the Sync Committee. And it's basically the way to think about this is that instead of having 400,000 validators running consensus on the chain, you select a subset of 512 validators, which are chosen randomly every 27 hours. And basically, these validators will just sign each block header, and if enough of them vote on it, it's considered valid. Now, the trade-off here, obviously, is that at the cost of it being easier to verify, you obviously have much weaker security guarantees, as you're assuming that 2/3 of these validators are acting honestly. So we explored this method at first to see whether we could basically build a light client on chain with just like these 512 validators. But we found basically in practice is that even verifying this consensus mechanism on chain is too gas expensive. Now, the practical reasons for this are that you have to store these 512 validator public keys and prove that they validly rotate every 27 hours. There's also this problem, again, which I mentioned previously, where we don't support the elliptic curve operations currently on the EVM needed for these signature schemes. So for every header you want to finalize, you might have to do up to 512 curve additions and one final pairing check on chain. So what's our solution? Well, our solution is basically to use the technology that ZK Summit is all about and to leverage the power of succinct zero-knowledge proofs. So what I mean by that is that like in your smart contract, you're going to have some function that's validating new blocks. And in practice, what we're doing in there is some pre-processing step, some check that the current validator set is valid, and then finally we check like the aggregation and the final signature check. And as I mentioned multiple times before, the big two challenges are these two bottom functions that I highlighted in red. And essentially what we can do is that we can move all of this expensive compute off-chain, just wrap it up into a zkSNARK, and what we can do instead on-chain is just verify this super easy to verify Groth16 proof on-chain, and that basically makes it super gas efficient to run these light clients on-chain. And I think like more broadly speaking, while we did this design originally for the ETH2 Sync Committee, you can essentially think of this as a roadmap to basically creating light clients for a wide variety of consensus protocols, including full Ethereum consensus. And I think this is really exciting because we're obviously seeing how zkSNARKs are being used to scale the execution and throughput of blockchains. But we're also now seeing how zkSNARKs can scale like the interoperability and composability of blockchains by making it easier to verify the consensus protocols that these blockchains run. So we're calling this basically like proof of consensus cross-chain communication or proof of consensus bridging. And essentially the idea again is to use these zkSNARKs to generate a validity proof of the state of the chain. And we basically believe that this sort of bridge design where you're running light clients on the target chain that like can trustlessly prove the state of the source chain is sort of like the end game design for trust minimized interoperability.
Okay, so John talked about the high-level approach, and now I'm going to dive into some more technical details, in particular to the implementation we did for the Ethereum Sync Committee. So as John previously mentioned, the Sync Committee does two things. Members of the Sync Committee for each header they generate a signature. They generate a BLS signature for each header they believe to be in the canonical chain, and then that signature gets aggregated. And so for each header, there's an aggregate BLS signature from validators in the sync committee and a proof that we generate of that signature being valid. The other thing the sync committee does is every 27 hours, it rotates its members. It's important it does that for security reasons. And so the current sync committee basically signs off on the next sync committee public keys. And we have another SNARK that basically validates this rotation. And we have a trick we use in there to reduce gas costs so that we never have to actually post the sync committee public keys on chain, because that's expensive. So yeah, we have two SNARKs, one SNARK that verifies this BLS signature is valid over the header, and the other SNARK that validates this rotation. And without going into too much detail of the SNARKs, basically we have these two SNARKs, and we had to develop a suite of primitives that we built in Circom to actually generate these proofs. So I'm gonna just go over some of the primitives we had to develop, and we hope that it's like generically useful for future work. So the first primitive is BLS public key addition to get the aggregate public key of all the sync committee members that are signing and generating a proof of aggregate verification. The other primitive, we worked really closely with our collaborators at zkSNARK over the summer for implementing pairing inside a SNARK, and we use that primitive to verify the BLS signature. And so one thing to note here is all the arithmetic we do for the pairing and elliptic curve stuff is done in the BLS 12381 field, which is different than the field that we're doing the arithmetic in the SNARK, so we have to do this out-of-field arithmetic. Other primitives we had to implement were the commitments to the SNARK public keys, or commitments to the sync committee public keys. So we had to implement simple serialization, which is what Ethereum 2 uses for serialization, SSZ for short. And we also implemented a SNARK-friendly commitment to the public keys with the Poseidon commitment. So I had previously mentioned this trick we did for reducing gas costs of storing public keys on chain. So just at a very high level, SNARKs have public keys and SNARKs have public and private inputs. And the public input is in red because it's bad, because that means if we're verifying a SNARK proof on chain, we have to store the public inputs on chain. And a private input is in green, and it's good because it's invisible on chain, so we never have to put it on chain. So naively, if we were to implement verification inside a SNARK, we would have to have the public keys as public inputs, because we have to check that the signature is from a known set of validators, right? Unfortunately, as I mentioned, storing public keys on chain is expensive, also because the set of public keys in the sync committee rotates every 27 hours. So we decided, what if we just store a commitment to the public keys? So you basically hash all the public keys together and store this commitment on chain, and then inside your SNARK, you prove that the public keys, which are now a private input, belong to this commitment. But because the sync committee rotates, we have to update this commitment, and it's not super clear how to do that. So one idea is when the current sync committee signs the next sync committee, they actually sign a SSZ serialization of the public keys. So one idea is we just use the SSZ of the public keys as the commitment, which is pretty simple. But the problem is that the SSZ is very SNARK unfriendly, and so it's super expensive to compute in every header verification SNARK. Because SSZ is just a bunch of SHAs, which is very SNARK unfriendly hash function. So our idea was, when updating the sync committee, we would verify a proof that would take in the new public keys, assert inside the SNARK that it corresponds to the SSZ serialization, and then also compute Poseidon serialization of the public keys, which is very SNARK friendly. And with that, we were able to map the SNARK unfriendly commitment to a SNARK friendly commitment, and what we store on chain is just a SNARK friendly commitment. And what this gets for us is it saves us 70 million constraints, which is quite a lot, in every header verification SNARK. So yeah, hopefully this trick can be useful in other contexts as well. And just some benchmarks. So as I mentioned, we have two different circuits. The sync committee rotation circuit has way more constraints because of this SSZ thing I mentioned. But for both circuits, the total witness generation post-proving time is on the order of 4 to 5 minutes. So our methods are actually really practical. In Ethereum, you have to wait for finality anyways, which is 2 epochs, which generally is maybe around the 12 minutes. So on top of that, you have to wait an additional like 4 minutes for proof generation. And we think that more modern proving systems can reduce this time quite significantly, and so hopefully the delay is quite minimal.
Yeah, so we've been working on this for the past few months, and everything we described in the presentation, we've actually implemented. We implemented the light client, and we've also gotten like a prototype bridge working on top of it. You can go play around with it. I think now it's at just succinct.xyz. Fair warning, it's in beta, and the mobile support's bad. But yeah, here's just like a few. Here's just a few screenshots of it working. It's just like a normal token bridge demo. You just choose your network. You choose your token. You say how much you want to send over, and then you'll basically just submit a transaction. And then basically behind the hood, what's happening is you'll make a deposit on like Ethereum. And basically what you have to do is you have to wait until the light client on the target chain gets updated with a block header, which can Merkle prove your deposit. So that'll happen after like 12 minutes plus like the 3 minutes for proving. And then we'll submit a transaction to update the light client. And basically, to withdraw your assets, you'll just basically provide a Merkle proof, proving that your deposit is like validly represented in the ETH state root. And after that, you'll have your assets. And yeah, you can go play around with it. It's all online. But anyways, yeah, to zoom out a bit about like what the pros and cons are of like these like proof-based bridges are first, like obviously, because we're able to borrow the security of the consensus protocol in theory. Like in theory, you could borrow like the entire security of Ethereum here. Your bridge is going to have much higher security guarantees, especially when compared to existing bridges such as multi-sig bridges or bridges based on like smaller decentralized networks. Another pro is like in a world where there's like an operator implementation where anyone can generate proofs. Theoretically, for example, you could incentivize people to submit proofs on chain, and maybe they get like a small percentage of like the fees that the light client is making or something like that. And like for these reasons, it's just much more decentralized and I think aligned with a lot of the values we care about in blockchains. And like at this trade-off, there's obviously some cons. Verifying like a SNARK proof is obviously more expensive than just checking that like 5 out of 7 signatures, 5 out of the 7 validators have signed. There's also some latency that you're incurring because of the proof generation time, but maybe that can be reduced to like by an order of magnitude. And also in terms of like scalability, one challenge here is that for every change you make to a consensus protocol or for every difference in consensus protocols for different blockchains, you have to kind of like go ahead and like hand design your SNARKs, and maybe you have to get them audited and stuff. So that can be a huge developer bottleneck for building these type of bridges. In terms of like our future roadmap, we kind of want to become like a trust minimized and decentralized interoperability layer for Ethereum and other decentralized blockchains. And in the short term, we're actively working on building what we're calling these like succinct light clients for other consensus protocols. And we also want to start working on moving away from the sync committee, which only has a security of 500 total validators, and work towards a world where we can verify all 400,000. Furthermore, we sort of want to also explore applications such as governance and identity outside of token bridging. But yeah, that's what we're thinking for now. Before we end, I just want to give a big thanks to Gnosis DAO, who was generously funded us a lot for this work, and also Xerox Park, where we worked out this summer, and we borrowed a lot of ideas from the people there. And yeah, that about wraps it up. If you want to collaborate or if you have any comments or thoughts, I'd love to hear them, and come find us afterwards. But also, if we have time, we can take questions now.
So we have about a little bit over 5 minutes if anyone has any questions for Uma and John. Yep. All right.
First of all, congratulations and thanks a lot for doing this. This was way overdue. This like should have, yeah, awesome. You guys are pushing this. Just maybe if you could. So you use this sync committee from E2. Can you elaborate a little bit more how you prove that this next set of signatures is constrained to be the correct one? Just to get questions started.
Yeah, so the current sync committee signs the public keys in the next sync committee, or they do something very equivalent to this. So you just have to verify that the signature of this header that includes these next sync committee public keys is valid. And then, as I mentioned with the trick where we map this like commitment to the public keys from being a SNARK friendly commitment or SNARK unfriendly commitment to a SNARK friendly commitment, that's just to reduce the gas costs of not having to store these public keys on chain. Yeah.
Great question. Are there any more questions? In fact, there should be more questions. If there's like nobody who has any questions, I'm shocked. I guess you did such a good job that we have. Oh, all right, there we go. Haha. I think I saw Henry. Oh, okay. No, Nick, it's, sorry.
Just quickly on that, maybe you mentioned it, but I could have missed it. So how do you handle equivocation if the current sync committee signs multiple seeding ones?
Sorry, could you repeat the question?
Yeah, but if they sign multiple disjoint subsequent sync committees to follow them?
Oh, like this is he's saying like if they basically double sign.
Oh, yeah.
Yeah, so currently the sync committee, there's a honesty assumption on the sync committee where if they double sign, they're not penalized for this. So you have to assume the members of the sync committee are honest. Of course, if you validate full Ethereum consensus or like validate like some subset of Ethereum consensus using like the duties the validators normally do, then you don't have to worry about this problem. So the assumptions of a sync committee are definitely a lot stronger than the assumptions on full Ethereum consensus.
Hey, so this is kind of a philosophical question, but do you think that it's better for decentralization overall to have a consensus protocol that has many, many validators, but no real practical light client, or one that has a fewer number of validators, but where the light client is very easy to run on any device?
Yeah, I think this is one point Uma made like a few times to me, but I think basically having a lot of these, I think in principle, like having one big network, decentralized network is probably better. Like I think the Ethereum and rollup future is actually like pretty secure and pretty nice. But I think one thing is like basically having multiple of these L1s is a point of like meta decentralization, where maybe you don't have so much lock-in into, for example, the EVM, or for example, like you're too much relying on like the ETH consensus protocol like operating correctly. And by having like many of these other L1 chains, you can sort of hedge against sort of bugs being introduced into a piece of software that's so important. I don't know if you have any comments.
Yeah, I think also your point about it's, you know, in other consensus protocols, maybe you have like less validators or something, and it's easier to have a light client. I think if we accomplish one of our goals, which is to verify all 400,000 or, you know, someday maybe it's more Ethereum validators and verify all of their signatures and verify the consensus in a SNARK, then you can have a light client with a lot of validators. So I think this is kind of like working towards that future as well. Obviously, it's, you know, technically very, very complex, but I think it's possible if we're able to do it, yeah.
Cool. I guess I'm all the way back here, but are there any last burning questions? No, all right.
Hello, guys. Do you still use Growth 16 as your ZK proving system?
Yeah, we use CirCom. We used CirCom to make these circuits, so that uses Grot 16. Or I guess it also has Plonk, but we use the Grot 16 version. But one of the main benefits of CirCom and Grot 16 right now is that it has a really stable, really trusted, used on-chain verifier, like for example in Tornado Cash. So it actually makes it practical right now. But as like these newer generation of proving systems get more proven out, especially with ZK-EVM and stuff, we definitely want to like re-implement this stuff and get all the efficiency advantages.
Thank you.
We've got a question from the chat, the live stream chat, all the way back here.
All right, go for it.
Jeremy asks, if I make a malicious ERC20 token, for example, only transfer to my address on one L1 and bridge it to another, does it emerge as a, quote, normal ERC20 on the second L1? Does sync committee check code?
Yeah, I think this is like a problem any bridge has or something. So I think most bridges like deal with the sync committee does not check code. Yeah, like we're mostly making this like cross-chain communication protocol for getting one chain state on another chain state, and then what you do with that, if you choose to make a token bridge, like you have to figure out like what cases you're going to handle.
All right, well, let's give it up one more time for Uma and John.